Okay, so just brief answer to this quiz question is you can explain Dutch-Jones algorithm with this circuit, and the problem is you want to find whether your function is balanced or constant, which is sending n-bit string to 1-bit string. And the way it determines the balanced or constant is you read off the input register after running the circuit once, and if all the measurement is 0 for the measurement outcome, then it's constant. If it's not, then it's balanced. So another remark is that you can solve the problem, this problem, computational problem, with single query, whereas the classical computer can solve this problem with at least exponentially many queries. All right. So today we're going to talk about the quantum Fourier transform. So I will define what quantum Fourier transform and give a little bit examples. And we also want to talk about the original Fourier transform and see what's the difference. So it's going to be written as QFT. The QFT itself is the unitary gate. It's a symbol of unitary gate. So it acts on n-qubit state. Well, of course, you can act on the 1-qubit state. So whenever you want to apply a quantum Fourier transform, you need to fix the size of qubits. And if it acts on the n-qubit state, say this is the base state. I'm not saying it's the superposed states, it's just the one base state consists of zeros and ones. Then it's defined as 1 over 2 n over 2 y from 0 to n minus 1 exponential 2 pi I to n xy y. So you're making it into a superposed state of all base state with a different coefficient. So maybe same, but mostly different. But the coefficient looks very weird. It's not the number. It's a value of exponential with the imaginary number inside. So therefore, it's a complex number. And it's very resembled with the Hadamard. So let me give an example. So I'm going to just apply this formula one by one to the most simplest quantum state you can think of, the zero cat. And so in this case, n equals to 1. So I have 1 over square root. And my y in the sum n runs from 0 to 1. And I have exponential 2 pi I times 2 xy y. So in here, x is 0, so I have 0 times y. Right? So when y is 0, exponential 0 is 1, so I get 1 over square root, 0 cat. And what happens when y equals to 1? It's still 0, so it's 1. The coefficient is 1. So I have a plus cat. So that's one of the base state for 1-qubit state. So let's apply to another base state, which is 1 cat. So 1 over square root y from 0 to 1 exponential 2 pi I. So in this case, it's 1 times y to n as 2 times y cat. And when y is 1, exponential 0 is 1, so I get 0 cat. But when y is 1, what happens? It's pi I, not 2 pi I, right? Exponential pi I is minus 1. So I get minus 1 cat, so which is minus cat. So when QFT applies to the 1-qubit state, it is exactly the same as Hadamard. So in other words, you can implement the quantum Fourier transform on 1-qubit state by applying Hadamard. Okay? So quantum Fourier transform is not a fixed quantum gate. It's a unitary gate that you have to implement. And in the 1-qubit state case, it's just Hadamard. So QFT TP on 1 qubit state can be implemented by Hadamard. So before we move on to see what is quantum Fourier transform acting on several qubit state, so let's think about why the quantum Fourier transform is defined this way. Well, the original reason is just because Shor invented this, and that's how Shor defined it. But so whenever you want to understand something, you have to understand what's the idea behind of that definition. So we need to go through the Fourier transform first. So what is Fourier transform? So there are two types of Fourier transform, if you recall any of material in the engineering mathematics 2 or other engineering courses. There are continuous Fourier transform and there are discrete Fourier transform. So continuous Fourier transform, both Fourier transform has the same purpose. It wants to change your time scale into frequency scale. So in other words, time space to frequency space. What does that mean? I want to see the data. I want to observe data or continuous graph, and then and suppose that graph is given by according to the time. So in other words, horizontal axis is time axis. I want to see the period. I want to see the frequency of that graph and see the periodicity of that graph or data. So you can start working with any of this Fourier transform, but it is easy to work with a discrete case. So I'll describe it here. So suppose we have a time scale from 0 to L. So L is the maximum amount of time you observe some data, and along this time range, you observe some data at certain moment. So let's say the beginning of time, it's x0 time, and so whenever you measure something, you can't really measure continuously, right? So in the real life, so you always have to have an interval, and suppose that we have a equal interval for every measurement time. So x1 and x2 and so on. At the end we have xn. So there are total n subdivisions or subintervals, and the length of this measurement interval is L over n. Okay, so you take a measurement, and you kind of want to assume that this is periodic. Okay, so because I want to find the period, so I want it to be periodic, but you don't know what the frequency is or what the period is. So what we assume is that we want to find out some pattern out of this at each time, at each point of time. So let's say at this time, so this is time, not the value, and not the data. We observe the data f0, and at time x1, we observe data f1 and f2 and up to fn. But we're kind of assuming that this is periodic, so we want to assume that this is originally back to the first data. So we only want to observe up to n minus 1. So fn minus 1. So the effective data that we want to analyze is n data, the first n data. This one, and this one, here up to here, not the last one. Okay. So what do we want? We want the periodic estimate, and the function, the elementary function that is periodic is sine and cosine. So we want to break it down into the sum of series of sine and cosines. So I want to set a polynomial px, which is the sum of sine and cosine. Let me write it this way. So first cosine and sine something. Okay. So there are things that I need to determine here. So when I use the cosine, of course, I need certain period of that cosine. So I need something going here. So before I plug in x here, so I need to determine what kind of cosine function or sine function that I want to look at. So first, you have, in order to determine this periodic function, you need to determine the amplitude of that periodic function. So let's say this is an, and let's say this is bn. So whatever n is, okay, so n must be some index running through this big sum. And for each n, I need to determine the period of cosine and sine. But when you look at this data, since you only measured in the time interval, the smallest time interval you measured is L over n, you cannot really find the period less than this much, right? So this is the smallest chunk, smallest times range that you can find the period. So for example, if all the points are, all the data are the same, that means, okay, maybe something might going on in between x0 and x1, but it must be periodic. That's your possible conclusion. But you don't know what's going on in between these consecutive time. So the smallest period you can think of is L over n, right? So n is going to, and also what's the next smallest, second smallest is this much. You have a two times step. That's the second smallest period you can detect, and third and fourth and so on. So in principle, when you take the discrete Fourier transform, you take the half, because if you pass over the half, then you cannot guarantee that this period is happening again, because there's not enough data for the second half. So you have to take the half. But here, we'll just take as an abstract situation that we can somehow know all the period from one time scale to the entire time scale. So what does this should be? So when you have just 2 pi, then it's so you have to rescale your period. So originally, if you have cosine x, then the period is 2 pi, but I want to rescale it, so I want to be, let's see, always confusing. So it's L over n. Okay. Then same for here, 2 pi n over L. So when, let's see, n could be 0, yes. So n, if n goes to 0, then you're looking at the constant function, as I said before. So n could be 0, but it also could be up to L minus 1. Sorry, n minus 1. Sorry. I think, let me check. They're always confusing. So here. Yeah, so it's right. So it's n. Yes. So n minus 1. Right. Right. So basically, I want to see whether period happens with a 0 period, that means constant, or 1-step period, 2-step period, and so on, up to n minus 1-step period. Right. So if I can determine an and bn, which best estimate these values f0 to fn minus 1 with this function p, then I'm good. So that's the best I can do. But I can simplify this formula a little bit more. Assuming that an and bn are not just a real number, it could be a complex number. So if I say bn, instead of bn, let's say bn over I times I, right? And I can rescale and then combine this together. So I can rewrite n equals to 0, n minus 1, and an minus bn I times, I think it's better to do it this way. So sorry. So let's put it Bn here. Just leave Bn here, and let's rewrite the cosine part here again. So how do I write it? With a exponential symbol. So here I'm going to use the Euler formula. I think we introduced in the beginning of class. So EI theta is cosine theta plus I sine theta. So this is same as EI, everything here, 2 pi n over L and x plus E minus I, 2 pi n over L x, and then divided by 2. Okay? And then do the same thing for sine. So in this sine case, these signs are opposite. So you get the same thing on left and right, and also 2. So in this case, not 2, it's 2i. Okay? But everything is same. Okay? So it's a bit complicated, but I'm not really picky on what the symbol AN, BN means. So once you mix up everything, what we get is n from, so in this case, you can see that the index is running from 0 to n minus 1, but the index inside of exponent of exponential function is becoming minus n to n. So you can say it's minus n plus 1 to n minus 1 of something e to the power of 2 pi I over n L n x here with some coefficient here. So this coefficient is determined by combining the coefficient we have here. I don't want to express it in terms of a and bn because it doesn't mean anything. So I'm going to write it as a cn here. Okay. So what do we have? So I have a px started from the periodic function, but later I have an exponential function of cosine of imaginary exponent, and the sum runs from here to here. But then I immediately know that I don't really need the negative part, right? Because if I have a negative part, it's just the same periodic function reverted. Like maybe same cosine function, or just the sine function with a different sign. So I'm just doing it twice. So it's redundant. It's not giving any new information. So I can just get rid of the negative part and then remodel this function p, and I'm going to write p as n from 0 to larger than minus 1, cn exponential. So now let's write exponential this way because I don't want to write exponent as a superscript every time. So we have L 2 pi I n x. So what do we want? So I want this to be the best predictor of my data measured at each time, xi. So let's plug in xj here. So I'm not going to write I as an index from now on because I is already used as an imaginary number. So at least if I want to predict the data, this value, pxj, must be the same as the observed data, fj, right? So cn exponential L 2 pi I L equals to fj. And what is x here? So x is xj. So it's the jth step. So we have L over n times j. Right? So we have L cancels out. So what do we have? N equals to 0, n minus 1, cn exponential, n 2 pi I, n times j. That's it, right? So it's kind of similar, right? Now we can see some similar thing going on. So you have exponential 2 pi I something as a coefficient, in this case, of the n qubit state. And in this case, we have Cn. So in the Cn, it's the strengths, in a quotation mark, of the frequency. So in this case, frequency is, what is the frequency? It's always confusing. It's J over N, right? So if you want the frequency of this much, then we need to, so if you see the strengths of that frequency higher than any other frequency, then you can conclude that this data follows mostly the periodic function with that frequency, right? So similar to that, so not exactly the same, but what quantum Fourier transform is trying to say is that we try to get the coefficient similar to the original Fourier transform and see what all the other quantum states are about. What about this y state? What about this number y? Do we have some information about the period by looking at this coefficient? Yes, we will, but not right now. We can't really see it as much as we can see from this Fourier transform. But you can see the idea where this coefficient comes from. So it's the same line of idea of the Fourier transform. So we can go a little bit more, but I don't want to talk about this much more because you can just get the idea and forget about the Fourier transform in the quantum Fourier transform case. It's not going to be directly connected to the Fourier transform, but the ideas are the same. The ideas are the same. So let me make a remark, write the remark here. So Fourier transform is basically period finding. So what we're going to do with the quantum Fourier transform, well, there are many other applications of quantum Fourier transform in chemistry or physics or AI even. But in our case, what we are going to introduce is the Shor's algorithm. And if you watch the video of Shor's interview, and Shor really explains why, motivation of his algorithm. And he didn't mean to search for, let's say, factorization. It was not his first motivations. His first motivation was to find the pattern of some lattice using the quantum circuit. And he thought about the quantum Fourier transform, and then he solved it. But later, people found out that maybe this looks like it can be solved. It can be used to solve the factorization problem. So Shor's original motivation is also period finding. But then this leads us to factorization. Because of the Fermat theorem. So Fermat theorem is so one way you can break RSA code, and this gives you the theoretical background why factorization is solvable by finding the period of a number. So that's the idea. You can just remember this and forget about the Fourier transform itself. Any questions here? Fermat, for Fermat. Theorem, THM. Sometimes it's called Fermat-Little theorem. There are many Fermat theorems, so you have to distinguish, but I'm not that picky on this. All right, so let's give another example of Fourier transform. let's apply to 2-qubit state. So what I mean by 0, 2, it means that I have 0, 0, right? So in this case, n equals to 2. So our coefficient is 1 over 2. And my y is running from 0 to 3. And the coefficient here is exponential 2 to the power of 2, 2 pi I times 0 times y, y2, right? So because of there is 0, every coefficient is 0. I mean, every coefficient is 1. So we immediately know that this is 1 over 2 of 0, 1, 2, 3, right? And let's write this way. So this is same as 2, 0, 1, tensor product, 0, 1, right? So it's not entangled state. So then let's apply to 1. So this is basically 0, 1. And by simply applying the formula, we have y equals to 0 to 3 exponential. Since it's 1, we have 2 pi I y over 2, 2, and y. And let's think about the coefficient. So when y equals to 0, it's basically 0. And when y equals to 1, it's pi I over 4. Right? Pi I over 4. What is exponential pi I over 4? Sorry, it's pi I over 2. Sorry, so I made a mistake. So it's pi over 2. So it's I times 1. And when y equals to 2, it's pi I. So exponential pi I is minus 1. When y equals to 3 is 6. Sorry. It's 6 over 4. 6 over 4, 3 over 2. 3 pi over 2 is what? Minus I? Sorry. Okay.
Because of 3 over 2, the exponential term equals to 3 over 2.
Yeah, 3 pi over 2, 3 pi over 2. Cosine 3 pi over 2 is 0, and sine 3 pi over 2 is minus 1, so it's minus I, yes, so it's 3. Okay. So can you also make it into the tensor product of 2? So let's try it. So it's 1 over 2, 0. Well, let me write it again with this notation. 0, 1. And 1, 0, minus I, 1, 1. Okay. So I can say 0 tensor, 0 plus I, 1, minus 1 tensor, 0 plus I, 1. So 0 plus I1 is common here. So we can say this is 1 over 2, 0 minus 1, tensor, 0 plus I1. It's also tensor product, right? So you want to do the QFT2 instead. Let's try this. I'll give it time to do this. So compute QFT2. See what happens. So try to make it into tensor product. One over two. So here are the results. So that's a QFT of 2. And how about QFT of 3? Okay, so if you haven't finished the computation, you can try it at home. And let's think about this more deeper. Is there any pattern? Oh, it's hard to see the pattern right here, but I think there is at least the pattern of having a tensor product. So maybe we can find a nice generalized formula of the quantum Fourier transform on any n-qubit state. So let's think about what happens when I apply the quantum Fourier transform on any arbitrary base states of n-qubit states. So let's say we have x to be x n minus 1 up to x0 as a binary representation, and see what happens when I apply this. So just by writing the formula, this is what the tensor product or quantum Fourier transform is. 2n minus 1 exponential 2 pi I 2n and n times x here. Maybe did I use n here? Or I think I used y, right? So y, and y here. And let's break it down. So every y n is y n minus 1 tensor all the way up to y0, right? And in this case, y can be written as y0 plus 2 times y1, 2 squared times y2, and up to 2n minus 1 times y, right? So I'm going to plug that in into the exponent of exponential function and see what happens. So let's see. So quantum Fourier transform xn is now written as 1 over 2 n over 2. And I'm going to break it into tensor product of, now the index of y is going to be called j. So j running from 0 to n minus 1. And for each yj, it's either 0 or 1. And what I'm doing here is exponential of 2 pi I times 2 to the n. So I'm going to just split my sum of exponents inside the exponential function into multiple of exponential functions with each an exponent here. So 2 to the j times yj and times x and yj. Okay. So whenever I have yj, it's 0, right? Just 0. Everything is 0. So this is same as over 2 big tensor product j from 0 to n minus 1 of 0. That's when yj equals to 0. So when yj equals to 1, then it's exponential of 2 pi I over 2n minus j x times 1, right? So that's the QFT. So basically, it's inevitable to have a tensor product after taking QFT. And we can write a little bit further. We can simplify, not simplify, we can break it down into a little bit further here. So instead of having 1 over 2n over 2 at the outside, let's distribute that 1 over square root of 2 to every tensor product. So it's going to be tensor product of j from 0 to n minus 1, 1 over square root of 2, 0. And also, look at this exponential function. X is also written as a binary representation. So that means x is also x0 plus 2 times x1 up to 2n minus 1 xn minus 1. So I'm going to write that out here. So taking a index, let's say k from 0 to n minus 1. So exponential 2 pi I 2 times kxk over 2n minus j times 1. Okay, so this whole thing is just one big coefficient. So that's a QFT in a different formula. So let me do the computation of QFT on 2-qubit states again, where now the base state is given as just a variable x1, x0. And if I just follow this definition, what is it? So, so this is the big tensor product between two. Okay? So first one, both of them, it has 1 over square root of 2 as a coefficient. So this is when j equals to 1, and this is when j equals to 0. So although I have an tensor product, it seems like it has no order. We have to keep the order. So when j equals to 1, it has 0 plus what? So when j equals to 1, we start from the 2 to the n minus 1. Here n is 2, so we start from just 2. And we increase my k. So when k equals to 0, I have 2 pi I 2x0. And when k equals to 1, that's the final index here, we have 2 to the k, 2 here, up here. So it's 2 pi I x1 times 1, right? And how about here? So that's when j equals to 0. So when j equals to 0, we start from 2 to the n, which is 4. So and k from 0 to 1. So we have 0 plus exponential 2 pi I for, when k goes to 0, it's just 1 here, x0, and exponential 2 pi I for 2x1, right? When the k equals 1. Okay. So what happens, I can simplify a bit more here, because whatever x1 is, whether it's 0 or 1, it's an integer multiple of 2 pi I. So exponential of integer multiple of 2 pi I always becomes 1. So I can get rid of this part. So the coefficient only changes for the cat1 in the first here, and only depends on the value of x0. And here, now I can cancel this out. So it depends on the value of x0 and x1 independently. Okay? So whether it could be I or minus I, depending on x0, x1. So that's the formula. That's the general formula. And let's try to implement that as a quantum circuit. So if you have you can make any quantum gate, imaginary and quantum gate, as long as it's mathematically correct. But if you cannot implement it in a circuit, it's useless. But quantum Fourier transform can be implemented. So this is how it's implemented. So let's say we have 2 quantum registers, because we are dealing with 2-qubit state. And let's call the 0 qubit and 1 qubit. So this is the 0th place and first place qubit. So in the 0th place, we had quantum state x0 and x1, and for the 1 qubit here. And you see, in order to produce this state, what happens? So you have to be really careful about the order here. So this is the qubit 0 now. This is the qubit 0. And this is the qubit 1. Okay? So originally, your qubit 0 was at state qubit at the cat x0, and qubit 1 is at the cat x1. But then, after applying the quantum Fourier transform, your qubit 0 is turned into this way, and you see that it's determined by x0 and x1. But in the qubit 1 is now only determined by x0. So what you want to do when you really implement the quantum Fourier transform is you first swap. So in this case, it's a swap, but actually what we are doing is to reverse the order. But in the 2-qubit state case, you can just swap these two to get the reversed order. And then, now, look at the first case here first. So you want to change the, so you want to change so you want to change the qubit 0 into this state, and look how it's done. So first, qubit 0. Yeah, this is qubit 0. Yeah, first. So let's say, so first, since you swapped it, so at this moment after swap, your qubit 0 is now cat x1, right? So when you apply Hadamard on cat x1, it becomes 1 over square root of 2, 0 plus minus x1, 1, right? That's how we compute it for the previous quantum algorithms. And how do you express minus 1 to x1 in a different way? This is exactly the same as exponential of pi I x1, right? When x1 is 0, it's 1. When x1 is 1, it's minus 1. So exactly the same as applying Hadamard. So this is exactly the quantum Fourier transform in 1-qubit state. But anyway, so so you see what I'm doing here? I made up to this far. I made exponential pi I x1, right? So you two cancels out each other. So I made this coefficient. But I still have this coefficient, right? I still have this coefficient. And what I want to do is whether or not I need to multiply this number. If x0 is 0, then it's just 1, so I don't need anything else. But if x0 is 1, I need to multiply this. So let's define R2 to be a unitary gate defined as this 2 by 2 matrix, exponential 4, 2 pi I. I think you saw this already. What is this? It's a square of z. So it's kind of a z gate, but you're not rotating pi degree, it's rotating by pi over 2 degree. So you're like half applying the z gate. If you apply full angle of z gate, you get the z gate, but you get just half. So you rotate around the z-axis by only half angle clockwise. So anyway, so if I have R2, then if I apply R2 here, so R2H on X1, then I definitely get, so need to forget, I cannot forget 1 over square root 2 here, 0 plus exponential this 2 pi I over 4 times this exponential pi I x1, 1 cat, right? So I want this when I have x0 equals to 1. Only when x0 equals to 1. When x0 equals to 0, I don't want this. I don't want to apply R2. So what do? I need to apply the control gate. So remember, still I'm here. So first I apply Hadamard to get this state, and then I have to determine whether I apply R2 or not by looking at the value of x0. So where is x0 here? Since I swapped it, it's in here, in this register. So looking at this quantum state and apply this R2 gate, depending on whether the value of x0 is 0 or 1. Okay? So that now, after doing that, I made the qubit 0 state, just as this. And how do I make this qubit 1 state? I just need to apply this, I apply this coefficient depending on x0. And you see 2 cancels out, and this is exactly same as minus 1 to the power of x0. So that's just a Hadamard gate. So that's the quantum Fourier transform, the circuit of quantum Fourier transform.
Where to measure the results?
Well, measuring is not happened yet. So this is kind of some small part of a big quantum circuit where it has a quantum Fourier transform in it. So you can, let's say, you can take this whole chunk. This whole chunk is now replaced by QFT. Just like when you have a Simulink in the MATLAB, you can make your whole circuit into a small, black box, right? So you can abbreviate your entire thing going inside as a QFT box here in your quantum circuit. Okay, so I think we're out of time, but yeah. So we can extend it to n-qubit state, but I just want to emphasize, just make a small remark. Whenever we apply quantum Fourier transform, we need to swap the qubits to reverse the order. So here, swap. So for example, if I have x0 state and x1 state, so how do I swap? How do I use swap to reverse the order? So I want x0 to be the bottom, x1 to be the top, and xn to be the top, x1 to be the one above from the bottom, and xn minus 1, xn minus 1 here, xn minus 2 to be the one below the top here. So I just used, so here, swap operations many times here, right? So let's say, so then if I apply the swap gate, these much, then I finally get every quantum state swapped, right? And then you want to do the similar thing I just showed you here for making a quantum state as same as the quantum Fourier transform, quantum Fourier transform. So the reason why I emphasize this, we often forget about applying this when we really want to implement into quantum simulator or real quantum computer to implement quantum Fourier transform. So I just want to make sure that you don't forget. All right, so next time we'll talk about more about quantum Fourier transform. And before we move on to the Shor's algorithm, I'll explain more about the RSA encryption and also Fermat's theorem, and see why Shor's algorithm is effective to factorization. See you on next. We have class on next week, right? So see you on next Monday.